So sorry for the long absence. I've been doing a lot of weird little projects and nothing really seemed to be video worthy, but I'll go ahead and cover some of what I've been doing now. One of the things I've been doing is finding random electronics at thrift stores and seeing if I can do anything with them. And an easy target is Wi-Fi routers, given that I've already done some work using those MediaTek Wi-Fi router chips. OpenWRT's website is great for dealing with these sort of things, since they're trying to flash new operating systems onto them, and they often have tons of info on how to access them in general. So first off is this little Linksys router. These are still sold brand new, or at least ones with a newer version number. This one on the back says it's model number E2500 version 4. It has a MediaTek MT7628, which is pretty much identical to the 7688. If I remember correctly, the difference was the 28 had a different layout for the antennas, but other than that, the registers and everything else is basically the same. This thing I found at Goodwill, but I found a similar model on the shelf at Fred Meyer's nearby, so they can be bought brand new. The MT7628 can also be bought new in the form of a thing called a Vocore 2. It's a little single board, like Linux kind of toy that people sell. Has a lot of weird little features. One I came across today, actually, I guess is they're popular with racing simulators, so you could have like a dashboard on your controllers. So interesting use of them. But I was glad to find this because it let me actually test if my MT7688 kernel needed any modification to run on the 28. So first thing is to open up the case. Some of these are easier than others. They usually have some screws. They're typically like these kind of wood screw sort of things that just dig into the plastic. Sometimes you have to hunt around for them. In this case, they were underneath the stickers here. A couple little holes down there. There's also some clips that held it on. I don't really care about those. I tend to break them off, trying to get the lid off. And it doesn't really matter because the screws are more than enough to hold the lid on when it's done. But once you get into it, what you're looking for is a way to access the boot console, and that would be UART pins. So in this case, they're right here. I soldered some pins on. They were just some through holes. It's one of the things the OpenWRT is nice about, is that since they're trying to do the same sort of thing, they often include pictures on their site and marking out which ones are the ground, the transmit, and the receive. Once you find the UART pins, you're going to need something like one of these. It's a little USB to UART dongle. You can also use like a Raspberry Pi. You just sort of wire ground to ground. You do transmit from one to the receive to the other, and then receive to transmit. So you kind of cross them. OpenWRT's website is pretty good also about telling you what speed that they run at. But if you don't know, you can kind of just test. Basically, there's two common speeds. One's 57,600 and 115,200. Some of these dongles will go up to 1.5 million, but there's not a lot of boards that actually use that as a standard. So the first time you fire this thing up, you'll want to keep your hand on the power plug, because it's going to, U-boot's going to come up and it's going to want to go into the default, basically whatever operating system's on it. So let's try that now. Alright, so let's plug this thing in and see what the UART outputs. Alright, and I'm unplugging it. And the reason I did that is because it's going to just default after this countdown and load up the Linux or whatever that's on here. And I want to know what I need to do to not do that. So it says, looks like 4 here. Will let me enter the command line interface. So I'll plug it back in. And there we go. So from here, one of the first things you can do is gather some information from the U-boot prompt, which is print env. So this will have some information on what this thing is already kind of set up to do. So here's the boot delay, where it's going to output stuff to. So yeah, the default is going to be 3. It's going to boot via flash. But you'll notice there's already some IP addresses in here. This is usually one of the ways that people would get OpenWRT and stuff onto these routers in the past, is they have like a system to download operating system images off a network. So we can actually use that to our own advantage. So in my case here, I'm going to be changing this IP adder value and the server IP. So I'm going to give it that. I'm going to set the server to my file server. I already have this thing plugged into the LAN ports onto my network. So I should be able to use TFTP to pull down a plan 999. So there it did. And then grab my MT7688 kernel. All right, and that loaded it to that location. There's a few ways you can boot things in U-boot, and the easiest one is to use the go command. It just tells it to go to an address and run whatever's there. All right. So now it's talking to the file server, and there it is. So now it's on the network. So I can go ahead and ping out to wherever I need to do. And now that the thing's on the network, I can actually access it from my Plan 9 grid like it's anything else hooked up to my grid. So I can rCPU host, it's called little router. Should be the owner. All right, which means I can actually just go ahead and run Rio now too. So this thing will probably have the same TLB miss problem that the previous ones did. Yep. So, yep. The MT7688 kernel does indeed work on the MT7628. So not much to that. But yeah, it was kind of nice finding this thing, because it at least let me know that those two were compatible. So if you are interested, you can, you know, rather than use the Onion Omegas or some of these other little Chinese router boards, I had the small little Linksys router, or the little Vocore modules that you can find at that website. I'll have a link in the description below for those. So another interesting project was this thing. This is a TP-Link. Goes by a variety of names. It says Archer C7 on the back. On the front it says like AC1750. When I looked them up on the internet, it seemed to go under a variety of names too. But it also has a MIPS chip, and it's different from the other ones I've worked on. If you watch my video about from the last IW9P, I had a little bonus bit about coming across a big Indian Atheros-based router board, the QCA 9531, if I remember correctly. However, both chips that I was working on were both the MIPS 24K type chips. The big difference was that the MediaTek one was Little Indian and the Qualcomm Atheros one was Big Indian. This one here is the QCA 9558, and it's a MIPS 74K chip, also Big Indian. It has the usual router parts, has a bunch of Ethernet jacks in the back. This one's kind of nice because it comes with a little push button switch for on-off power. Has a little on-off switch for the wireless. I guess you can cut off the wireless, but it's probably wired into a GPIO switch or something. Uses software to actually kill the Wi-Fi. 2 USB ports, little indicator LEDs for that. On the inside, here's the CPU here. There's onboard Wi-Fi, which goes to these internal antennas here. And then this mini PCIe bugger here, it's actually quite a large board for that, is another additional 5 gigahertz radio. So this does both 2.4 and 5 gigahertz. OpenWRT did have a listing for these little pins right here. I don't know if the camera will pick those up. I did solder some pins into it. They were just through holes, so there's actually like a JTAG ports here and then a UART one down here. But when I got those in and got into it, I couldn't actually stop the boot process. And it took a little bit of Googling, and what it turned out was that at the prompt, rather than hit some menu, option or hit any key to get into U-boot, I had to type TPL really quick. So I'll show that now. All right, I'll push the little power button on the back. And so I can hit any keys here and it won't stop. It'll just start booting Linux up. So I'll hit the power button, hit it again. And it's right after it does the Ethernets here. You type TPL really quick, and there it is. And now I have a prompt. So right off I went and looked up what I could, and this chip seemed to be very close to the 9531, which is sort of like how the 7688 and the MediaTek 7628 are practically identical. This thing was almost identical to the 9531. As far as where the registers for various things were, I didn't have to change anything to access the UART or the Ethernet. Manufacturers will often recycle various parts in a system on a chip like this. A lot of times they don't even make these things themselves, but they also license them just like they do with the cores. So I made a kernel for the 9558 that was pretty much just a copy of the 9531, and it wouldn't boot. It would get as far as making the jump to user space to run the initial boot RC scripts, and would throw an exception that I didn't have any code to handle. And what it turned out to be was that it was trying to double write TLB entries. So I can actually demonstrate that by just having it run the kernel for the 9531 here. So I'll change the environmental variables again to have it go fetch files off my file server. So loaded that, and then we'll do the wrong kernel here. We'll go ahead and jump to it. And it gets through here, and then, yep, as soon as it makes the jump to user space, it does this machine check core trap. So this definitely was kind of a bummer at first. I was kind of looking forward to this one because what I looked up, for one, it has gigabit Ethernet switch, which most of these other little routers, these cheapies, have 100 megabit. This one also has 32 TLB entries, unlike the other Atheros one, which is only 16, so it has less of that TLB miss issue. But this thing was actually throwing the exception, and that pointed to TLB entries being duplicated. This is very much a case of read the manual, as the MIPS manuals for the 74K chips laid out my exact issue. The original code base that I was using was a mashup of old MIPS code for a Silicon Graphics workstation and for the 24K based router boards. This chip introduced some newer technologies, and one of those was out of order execution. So I tracked down my TLB issue. Let's switch that to, here we go. So I tracked down my issue to this instruction here, this TLB-WI. So what this is doing is putting in a TLB entry, and this is something called from like the portable code. So this is why this was happening. When I made the jump to user space, this was additional programs now asking for virtual memory addresses. And so, it would enter in an index in the TLB, the virtual address, the physical address is a page mask. All that gets entered in, and then it commits the write. Now, the old way says that to make sure that like all these entries here were flushed through the pipeline before doing this, the old way to do that was just to throw some no-ops in, just to pad the pipeline out with that. And this part of the code here I borrowed from the old Indie kernel because it had sort of kept pace with the way 9Front handled asking for virtual addresses. And the 24K chip was close enough that I could still get away with it. In my case, though, the data was going in so fast that things didn't have time to actually be updated. And so instead of having two entries with different data, I would end up having two entries with the same data. The system would catch that, throw an exception, and basically, crash. Doing some testing, I found out I could write some code to catch that. One of the things that, let's see here, this machine check core thing would do is turn off the TLB system, so I could, trap the exception, turn the TLBs back on, and keep going. It would take the system about 5 minutes to boot, and then it just ran terribly after that. To fix this, I had to add hazard barriers to in between these calls here, and that basically is a system to tell the CPU to make sure it finished doing a write before moving on to the next instruction. And that would look, oops, forgot to clean out, make clean here. All right, be TLB right index. So here it is with these EHBs, and then the one combined in with the jump to return. So that would make sure that everything got written correctly. So with that whole TLB issue fixed, the thing more or less behaves a lot like the QCA 9531 kernel that I already have up on my GitHub. So, yep, there it is. Called up my file server. That means this thing's on the network. Yep, there it is. And just like before, I could access this thing from, my grid and Rio into it and all that. So yeah, nice little improvement there. I'll probably do some more work to actually fine-tune the networking on this thing. That's something I kind of didn't get to on the 9531. But this one actually has a gigabit switch, so it could kind of behave like an actual proper router for my grid. So keep an eye on GitHub, and I'll probably be uploading that one soon. Hopefully I can get some more performance out of it too. I did find some stuff from the people at FreeBSD mentioning some tricks to get a little bit more speed out of it. So we'll see how that turns out. So to stick with the theme of low-level stuff, I also got motivated to get a kernel running on this, the Odroid M1. This has been on my shelf for a while, and the plan was to make it into a 9Front file server. And this summer I had some fires and some power outages and some very hot days, and that made me want to get a start on setting up a file server that makes less heat and could also run off a battery backup. And I wanted to go all Korean on this build since Odroid, or this thing's made by Hard Kernel, which is a little Korean company there. Not sure if that comes up on the camera or not. So tucked in there is a little Samsung NVMe drive. And I wanted to go with the Samsung platter drive, but they sold their platter drive division to Seagate, so I went with the Seagate to plug into the SATA port on here. Anyway, it's a very interesting piece of hardware with some very annoying software. Rather than use the standard U-boot stuff, it uses U-boot to start a thing called petty boot, which is just a stripped down Linux. It's meant to use some Linux method for rebooting into another kernel. The upside is that all the Linux drivers are there, so it can load off the SATA or the NVMe or do a Pixie boot sort of thing over the Ethernet. And I was told 9Front works with this, but this petty boot from Odroid would not boot a 9Front kernel. And at this point in my life, I'm not that interested in learning new Linux stuff. So it got put on the back burner, but I got motivated again and started poking around. So the first thing I had to do was find a way to get serial console access. That petty boot wants to use a monitor because there's HDMI on the back and a keyboard plugged into the USB. And long term, I intend to use this thing headless because it's going to be a file server, so I really don't want to bother with having to do any sort of settings where I have to plug this thing into a monitor. So I tried various pins that were documented as being for UARTs on the board, and then added little bits to the boot to basically spam, a number to every UART to figure out which one was actually wired to which one on the board. And then I also found a way to keep U-boot from booting into petty boot, and in this case it's Control-C to get to the command line. Alright, so here I am in the boot console for the Odroid M1. As you can see here, it does say Control-C to actually stop the auto boot. So yeah, there's everything it does to start up the petty boot and all the other sort of things it does, which I'm not interested in. So this board runs a Rockchip RK3568, and I was able to find some data sheets for it a while back, so I had a rudimentary kernel already done for it, one that petty boot would fail to load. And when I finally got it through here, it sort of worked. What it failed to do was start up more than one core. So it was off to read the manuals again, and this is similar to my previous MIPS issue. In this case, my previous kernels were for the Cortex-A53 chips, and this one runs a Cortex-A55 chip, which of course has some small little differences. So when the system boots up, it'll run through a bunch of the stuff here, make sure the MMU is disabled, invalidate the caches, set up some basic stuff for the stacks, clean out a bunch of things, basically set everything to 0, enable the MMU, and then jumps to main. So it'll go to the main function, and this port's kind of important here. So here's where it checks for the mock number, which is the core number. So in this case, it's going to come up and that's going to be 0. Which means it won't go through this. It'll go down through here. So it does more setup and then gets to this MP init. So in here, this is where it starts the multiprocessor part of the core. And there's various ways to do this. This one's going to use this SMC call routine. And it's going to, this is the actual command to turn a CPU on. What this does is fetch the current number of the core that's running, which would return 0, and add 1 to it. So this for loop goes through and basically starts at core number 1. So remember, it boots on core 0. And then says boot core 1, goes through this loop, increments this, or boot core 0 or 2, and then 3. Because this, and number mock is set by a macro elsewhere to be however many cores you expect to have on the system. But what was happening was this would run, and what it does is it says jump to start. So it tells the next core, so when core 1 comes on, it comes back and starts here. And does everything it needs to. But what happens is it comes to this little part here, where again it checks this little register, and it asks, what number core are you? Stores it in R1. And when it gets down here, it says, if this is not 0, jump past all this stuff. But what it was doing was, it was reading this register here, and core 1 was returning that it was core 0, because it would proceed to go through here, which clears everything out and just locks up the system. So it was off to the manuals. So ARM offers a lot of documentation, arguably too much documentation, and not always in the best format. And being ARM, they do brisk business helping companies make custom chips. And you'll find a lot of things where it just tells you that the vendors might just do something different. So anyway, there's this register here called MPIDR EL1, which is this multiprocessor affinity register. ARM has a bunch of these sort of little registers that, with weird names that do all kinds of various settings. So I thought something must have changed since it was acting as if core 1 was being read as core 0. So I had both the the pages open here for the A53 core and the A55 core, and it seemed like they were nothing really changed. They're both laid out the same. What I'm interested in is these first 8 bits here. So if we go back to the the code here, we can see it's actually masking out the value here, and over in the right here, it's calling that again, just masking out the first bits and putting in the index number. So, I went reading through all this stuff. Oops. I happened to be on IRC at the time, complaining about my my troubles here, and shout out to Synap because he's the one who caught this. All the way down at the bottom here, it mentions that first block, those 8 bits, a affinity 0, that these are now not used for cores, but for threads. So affinity level 0, this level identifies the individual threads within a multi-threaded core. But of course the A55's core is single-threaded, so this value will always be read as 0. They had moved the core value, because this one will tell you that this will give you a number for a core. So affinity 0, single core, 2 cores, so many cores. but here they moved that to affinity 1. So this becomes the identification number for each CPU in a Cortex-A55 cluster. So the solution is to use the affinity 1 bits rather than the affinity 0 bits to call each individual core. In the mpinit function, this is pretty straightforward. It just runs through this loop, checks it against the number of cores and called from there. And so all I really had to do was shift that value over 8 bits so that it would use affinity 1. However, this got a little bit trickier in the low-level boot code. So I couldn't just make this mask here bigger because core 0 would still be core 0, but core 1, when you shift a 1 over 8 bits, becomes 256, and 2 shifted over 8 becomes 512, and so on. So it would report that this is, you know, core 0, core 256, core 512, and so on. And there's some other little math that's done down here that uses that value that I didn't want to mess with. So what I ended up doing is I needed to shift the number back over the other direction, and I had to do it in assembly. And I'm not as familiar with the with ARM assembly, but I found another example in the 9Front code, and I knew register 7 wasn't being used because I'd be using it for waves. So long as I didn't do any waves within this block, I was fine. So I called that register to get dumped it into there, shifted that over 8 bits, dumped that back into register 1, and then everything could keep using the core number from register 1 from there on out. So, and that actually worked. So let's go ahead and fire up the U-boot on this thing and boot it up. All right, plug it back in, spam Control-C. All right, let's see, I gotta go. I need to grab a little text file here where I have all my stuff set up. So this thing here doesn't have, or at least for whatever reason, I'm not really sure why, whether it's just U-boot doesn't have a networking driver for this rock chip, or if Odroid just didn't include it in the U-boot that's on here, but it won't boot off the network. This isn't really a deal breaker because, again, this thing's supposed to be a file server. So in the long run, it's going to, other things are going to boot off it. So it's just going to actually have to load everything off the SD card and boot from that. So read that, and then go. And there it is. So again, I don't have the Ethernet driver done for this thing yet. So all I can do is get into, use the bang RC thing to get into just a basic RC shell. But I can, cat Mordor. Let's see, you can do dev, cat dev. There's all 4 cores. You can see they show up here. So I have to go through and do clock and gating code too to get all this stuff set up right, instead of running at 800 megahertz to get it up to whatever its maximum speed is. So yeah, I have a little bit of work there. Luckily, NetBSD does have a driver for the Ethernet this thing uses. It's not exactly right because theirs is for a different rock chip, so some of the registers are a little wrong, but it shouldn't be too hard to sort of tweak that and get it running, and hopefully soon do the Ethernet, SATA, NVMe and SD card drivers. This thing also has a little spot to put in a little flat battery, a little coin cell to run a real-time clock on it too, so I'll have to get that done. And then hopefully have a little ARM-powered fanless file server. Anyway, that's kind of some stuff I've been up to. Had just a lot of random projects going on this summer, so nothing really serious to show. Plans right now are to rebuild my grid and get everything updated to the latest 9Front release. I've slowly been working on getting a Wi-Fi driver done for the MT7688. So far I can load up the firmware, which is a start, but Wi-Fi drivers are kind of finicky things with 1,000 little settings. And I want to get the Ethernet SATA, NVMe and stuff working on that Odroid M1 so I can have a low power file server to work with. And as usual, have fun.